All right, so we are going to start a new chapter. So today you are going to learn chapter 6, and it is about work, energy, and power. All right, so let's start with work. So in our everyday life, work means doing something. Okay, so doing something means work. But in physics, doing something may not be the work. Okay, so what is work in physics? Okay, the work, to represent work, we use the symbol W, uppercase W. Okay, and it is defined as this. Okay, W equal to force times displacement times cosine theta. Okay, so the force work done is related to force, displacement, and what is theta? Theta is the angle between force and displacement. Okay, so to understand this, let's consider this picture. Okay, so here you see that we have a box. Okay, and someone is pulling with this force. Okay, so this is the force she is applying on this box. Okay, so by applying this force, she's able to move this box from here, from this position to this position. Okay, and as you know that displacement, okay, so in chapter 2 you learn about displacement, and displacement delta x was final position minus initial position. Okay, so here you see that there is a change in position, that means we have some displacement. So here in this chapter we are not using delta x for the displacement, we are using d for displacement. Okay, so by applying this force F on this box, she changes the position of this box by this. Okay, so the work done here is W equal to F, the force she applied, times the D is the displacement, and here angle theta is basically the angle between, you see that this is the force and this is parallel to the displacement. So this is the displacement and this is parallel to this line is parallel to the displacement, and angle is basically this. Okay, so if you draw a free body diagram, okay, a diagram similar to free body diagram, so you can write something like this. You can draw something like this. So here is the object. So she's applying a force in this direction, so this is F. Okay, and the displacement is happening in this direction. Okay, so you can see that this is the theta. Okay, so theta is the basically angle between the force and displacement. Okay, so that's how we define work done. So in physics, work done means force times displacement times the cosine of angle between force and displacement. Okay, although force is a vector quantity, displacement is a vector quantity, but the work done is a scalar quantity. Okay, so this work done is a scalar quantity. So this is a strange thing. Okay, the first strange thing is this, right? So earlier we see that when we deal with a vector quantity, the product is also, if you remember, for example, the force equal to ma, right? Acceleration was a vector quantity, so the force is also vector quantity, right? But here it is different. It is different because it is not the simple addition or simple subtraction or simple multiplication. It's something else. Okay, unfortunately we are not learning those things. Okay, it's called vector product. So there are two types of vector product: scalar product and dot product and cross product. But we are not going to do this here. So you have to just remember that although force and displacement are scalar quantity, the work done is a, sorry, force and displacement are vector quantity, work done is a scalar quantity. Okay, so work done is a scalar quantity. All right, now the standard international unit for work done is joule. Okay, so the standard international unit is joule. Okay, and joule is related to the meter and newton. Okay, why it is meter newton? because you see that W equal to FD cosine theta. So F is Newton and D is meter, and cosine theta does not have any unit. Okay, so that's why you can write Newton meter as the standard international unit of work done, but normally we don't write it. We use joule for the standard international unit for work done, and J for joule. Okay, so that means 1 joule is equal to 1 meter Newton or 1 Newton meter. Okay, all right. So the next thing is some special cases. Okay, so we just learned the general definition of work done, and that is this. Okay, but what happen if we pull the box like this way? So let's say we have, now consider this picture. Let's say we have this box. Okay, so instead of applying a force in this direction, let's apply a force in this direction. Okay, so by applying a force in this direction, let's say we changes its position from here to here. Okay, so the force is in this direction, the displacement is in this direction. Okay, so what is the work done now? Okay, so again, W is equal to F D cosine theta. Okay, but here you see that F is in this direction, D is also in this direction. Both directions are in the same in the same direction, right? Both point in the same direction. So when both point in the same direction, the theta is equal to 0 degree. Okay, and cosine 0 degree is 1. Okay, so work done for these simple cases becomes even simpler. So work done is basically FD. Okay, why FD? Because cosine 0 degree is 1. So we get a simple equation for work done that is just the product of the force and displacement. All right. So from the general definition of work done, we see that we can have a simple mathematical equation for the work done when both force and displacement are in the same direction. Okay. All right. Now let's move on and see what else we have. Okay. Now, as earlier I said that in physics, even if you do some work, do some everyday work, it may not be the work done in physics. Okay, so let's see some of the example. Okay, so for example here, so let's consider now this picture. Okay, so in this picture, so this person is holding a briefcase. Okay, briefcase has mass m, so that means it has a gravitational force, right? And it should be downward, mg. Okay, because you are holding it, that means you are applying some force against gravity. Okay, so that means you are applying some force F upward because the gravity is downward. So if you don't apply this force, it will not it will not be on your hand, right? So because it is stationary at your hand, that means you are applying a force against gravity. Because gravity is downward, that means you are applying a force upward. Okay, so here you see that you are applying a force, but you are not moving. Your displacement is equal to 0. Okay, so because your displacement is equal to 0 here, the work done is also 0. Okay, and it is simple to understand because W equal to FD cosine theta and D equal to 0 means work done is also equal to 0. Okay, so you see that that person is applying some force, but because the displacement is equal to 0, work done is also equal to 0. Okay, and that example is another same example is, for example, let's say this is a wall. Okay, and you are applying a force, you are pushing the wall. Okay, so you are pushing the wall. Now you know that wall is very heavy, so the displacement will be 0 Okay, so even you are applying some force, okay, because displacement is equal to 0, work done will also be equal to 0. Okay, so when displacement equal to 0, the work done is also equal to 0. All right, now another interesting example. Okay, so this one, let's see this one. Okay, so now here the same briefcase the person is holding, that means this person is applying some force in this direction. Okay, so this is the direction of the force, and the person is moving in this direction. Okay, so the displacement is happening in this direction. So you see here the angle between force and displacement is this angle, right? And this angle is 90 degree. Okay, and you know that cosine 90 degree is equal to 0. So because cosine 90 degree equal to 0, W equal to F D cosine 90 degree, and then it is equal to 0. So here you see you are applying, the person is applying some force against gravity, right? So there is a force, there is displacement, the person is walking, right? So changing its position, right? So there is force, there is displacement, but because the force and displacement are perpendicular to each other, I mean the angle between the force and displacement is 90 degree, so the work done is 0. So remember that work done can be 0 either when d equal to 0, I mean the displacement equal to 0, or when cosine theta equal to 0, I mean theta equal to 90 degree. Okay, so if theta equal to 90 degree, even you apply force, okay, then the work done will be 0. Okay, now another example of the 0 work done is the centripetal force. Okay, so in last chapter, in chapter 5, you learn about the centripetal force. Okay, so let's consider this picture. Okay, and if you remember from last chapter, the centripetal force or the radial force is always to the center of the circular path. I mean, we can have centripetal force when an object is moving in a circular path. Okay, so in this picture you see that the car is moving in a circular path, so there is a centripetal force to the center or along the radius. Okay, now in this case the displacement is happening to the tangent. Okay, so the here this is the tangent, right? The displacement for this particular position is this one, the direction of the displacement is this. Tangent and radius is always perpendicular to each other, that means this angle is 90 degree always. Okay, so because cosine 90 degree is 0, so the work done by the centripetal force is 0. Okay, because the angle between the force and the direction of the displacement is 0. All right, so now we see that work done can be positive. Okay, positive work. Okay, and we see that work done could be 0 for different cases. The last thing we want to understand is the negative work. Okay, so work done can also be negative. Okay, so to understand this, consider this picture. Okay, so the sled is moving downward, right? It is moving downward, so the displacement, the direction of the displacement is in this direction. Okay, now it is basically moving downward, so there is a friction between the sled and the snow, right? And as you remember, I mean, I believe you remember from chapter 4, the friction force is always opposite to the motion, direction of motion. So the direction of motion is this, okay, the direction of the displacement. So the friction force is in this direction, right? So because the friction force is in this direction and the displacement is in this direction, so you see this angle is 180 degree. The angle between the displacement and the force is 180 degree. right? This angle is 180. So now if you plug this value, okay, FD cosine 180 degree, and cosine 180 degree is -1. So then what we get is W equal to negative FD. So when the displacement and the force are opposite to each other, the work done we get is negative work done. Okay, so for example, the friction force does negative work. Okay, remember that. Let's move on. The next thing we are going to learn is energy. Okay, all right. So the first we will be learning basically kinetic energy. Okay, so energy has many forms. Okay, for example, I already mentioned kinetic energy. So in this chapter you will be also learning about the potential energy, in fact different kind of potential energy. Okay, and later in physics 2 you'll be learning about thermal energy, okay, and electrical energy. Okay, so energy has many forms. I mean, not only this form, there are there is a form called chemical energy, and then many other form. Okay, so because energy has many form, it does not have a particular definition. Okay, but in general, energy is defined as the ability to do work. Okay, so energy is defined as the ability to do work. Okay, we are not going to do we are not going to learn all the form of energy in this chapter. We are basically learning about the kinetic energy and potential energy, two forms of the potential energy. Okay, so let's focus only on these energies. Okay, so the combination of the sum of the kinetic energy and the potential energy is called the mechanical energy. Okay, so first thing we are going to learn is the mechanical energy. Remember that the mechanical energy is the sum of kinetic energy and potential energy. Okay, so we use E for the mechanical energy. Okay, E equal to sum of kinetic energy and potential energy. Okay, now what is the kinetic energy? Kinetic energy is the energy of motion. Okay, so when an object is in motion, okay, then we can have the kinetic energy for that object. Okay, so for example, if an object is moving with a velocity v, then the kinetic energy of this object will be this. Kinetic energy equal to half mv square. So m is the mass of the object and v is uh, the velocity. Okay, so if v equal to 0, then the kinetic energy is also equal to 0. Okay, so remember that an object, if it is moving with some velocity, then we can have the kinetic energy for that object. Okay, if it is at rest, okay, if it is not moving, the kinetic energy will be equal to 0. All right. Potential energy we'll be learning later, but let me just briefly define it. Potential energy is associated with the position of the object. Okay, for example, first we'll be learning about the gravitational potential energy, and gravitational potential energy is connected with the height of the object. Okay, so you will see it is related to the height of the object. Okay, for the time being, just remember that potential energy is associated with the position of the object. Okay, object's position. On the other hand, kinetic energy is the energy associated with the object's motion. If the object is at rest, there is no kinetic energy. If the object is in motion, there will be kinetic energy for that object. Okay, all right. Now I want to show you that work and kinetic energy are related. Okay, so work is related to somehow kinetic energy. So work is somehow related to kinetic energy. I mean, I'm not saying it is equal. Somehow this work done is related to kinetic energy. So I'm going to show it. So here I derive the equation, how they are related, but I'm not going to derive it here. If you are interested, just go through it. Okay, I'm just showing it in a simulation. which is easier to understand. That's why I'm showing the simulation, and then I will be discussing the final form. Okay, so let's go to the simulation and then come back here to discuss the final form. But if you are interested on the how I derive, just go through it. All right, so this is the thing we need. Okay, now as you know that when we apply a force on an object, if it changes position, that means we are doing some work, right? So in the first phase of our slide, we learn about that, right? So the work done, so remember that work done is equal to F D cosine theta. Okay, so here you see that we have an object here. Okay, a force is applied. Okay, so we are going, I didn't start it yet, so we are going to apply this force. So if it changes position, so now it's at 0 meter. So if it changes its position, let's say it moved to somewhere here. Okay, so that means it changes position, right? And then that means it has some displacement, right? Here we have some displacement d. Okay, and because here it looks like the angle between the displacement and force is 0, so the equation will be just Fd. Okay, so when we apply some force and if there is some displacement, okay, that means we are doing some work on this object, right? That we already learned in the first slide. Now here I'm going to show that by doing this, that the kinetic energy of the object will also be changing. Okay, so we are applying some we are doing some work on this object, and at the same time you will be seeing that there will be change in the kinetic energy. Okay, initially you see that the kinetic energy equal to 0. Okay, so here you can see also kinetic energy equal to 0, but as it will be moving from this position to here, you will see that the kinetic energy, so you will see that bar graph will change, and this number will also change. Okay, and for simplicity, I'm not considering the thermal energy here, so you will not see thermal energy here. Okay, at the end of this chapter we are going to introduce thermal energy, but for the time being we are neglecting the thermal energy. Okay, so thermal energy is basically due to the friction between the object and the ground, and we are going to introduce at the end. Okay, so now let's see what happened, whether kinetic energy changes or not by doing some work on this object. Okay, so let me start it and see that whether it changes the kinetic energy or not. So you see that we are currently the displacement is 5.5 meter. Okay, so here you see the displacement is 5.5 meter, and you see that there is a kinetic energy here, and also this graph, this bar graph. Okay, so you see that somehow work done is related to the kinetic energy. Okay, so you see that. All right, so you see that the displacement is 35.1 meter and the kinetic energy bar was 0. Now it is full. The current kinetic energy is 702 joule. Okay, so what we see here is work done work done is somehow related to the change in kinetic energy. Okay, so how you know that? Here you see that the kinetic energy is 702 joule, and if you want to calculate the work done, you can calculate the work done from this equation. Okay, so the force we applied is 20 Newton, and the mass of the displacement is 35, right? So we don't need mass basically for work done. So 20 Newton times 35.1 meter is equal to 702 joule. Okay, so you see that the work done is equal to the change in kinetic energy. Okay, now let me go back to the slide. Okay. Okay. So by doing the math, some simple algebra, I basically show it here that that the work done, the net work done is equal to the change in kinetic energy. Okay. So net work done is equal to change in kinetic energy. Okay. Or change in kinetic energy should be final kinetic energy minus initial kinetic energy. So remember the change or the delta of some quantity is equal to the final quantity minus initial quantity. It is always true for any change in quantity. Okay, so what we see here basically from the simulation, the net work done equal to the change in kinetic energy, final kinetic energy minus initial kinetic energy. Okay, now when the kinetic energy when the work done is positive, okay, so when the work done is positive, the kinetic energy increases. That means the final kinetic energy is higher than the initial kinetic energy. When it is negative, when the net work done is negative, that means the final kinetic energy is lower than the initial kinetic energy. That means the kinetic energy decreases. Okay, so yeah, you can see that from this equation. Okay, now because work and kinetic energy are related by this equation, the unit, the standard international unit for kinetic energy or for any energy is also joule. Okay, so the standard international unit for energies are joule. Okay, and it's also a scalar quantity. All energies are basically scalar quantity. All right. Now, this is an interesting simulation. Let me show it. Okay. So this simulation is basically show how the kinetic energy is related to the stopping distance. Okay, you can prove it by using the by using this equation. Okay, so W net equal to change in kinetic energy, and it has some special name. We call it work energy principle or work kinetic energy principle. Okay, so whenever we refer it, we will call it work energy principle. So what I am going to show in this simulation is that by using the work energy principle, you can show that kinetic energy is somehow related to the stopping distance. Okay, so let me explain what it means. Okay, so here you see that we have 4 cars. Okay, and this at the bottom here you see that the first car's velocity is v0. Okay, so this one is running at v0, and let's say v0 is 1 meter per second, and 2 v0, that means this one is running at 2 times 1 meter per second. This is running at 3 times 1 meter per second, and this is running at 4 times 1 meter per second. So that means this is this car is running at v0. This is at 2v0, twice the speed of the first one. This has the 3 times the velocity of the first one, and so on. Okay. Now, when the car is here in this break point, okay, when all the cars here at this point, okay, we hit the brake. Okay, break point means we hit the brake, and the force we apply is the same for all these cars. Let's say we apply same force F for all these cars. Okay, now here I want to show that when the car is moving at higher speed, the stopping distance, the car will stop at further distance. Okay, when the speed is low, the stopping distance is less. When the speed is high, the stopping distance will be high. Okay, so when you brake, so when you're driving a car in a straight street, okay, if your speed is high, then it takes time to stop car. So here I want to show you by using this simulation, and you can show it by using the work energy principle. I mean, you can prove it. Okay, so let's see. So you see that the first car stops at 1 meter. Okay, so let's say it stops at 1 meter. Let's say the unit for this axis is meter. Okay, so it stops at 1 meter. You see that it stops at 4 meter. It stops at 9 meter, and it stops at 16 meter. Okay, so you see that there is a relation between this number and this number. So here you see that 2. So here you see 1, and 1 square is 1. Here you see 2, 2 square is 4. Here you see 3, 3 square is 9. Here you see 4, 4 square is 16. So you see that the stopping distance is square of the velocity, right? So how to prove from the work kinetic energy principle? So you know that work kinetic energy principle tells us that net work is equal to change in kinetic energy, right? Change in kinetic energy is final kinetic energy minus initial kinetic energy. Okay, so final kinetic energy is 0 because car stops finally, right? So this is something like this, and this is equal to minus half m v1 square. So v1 means these speeds. Okay, and on the other hand, in the left hand side we have fd. Okay, so f is same for all the cars. So what we see here, d is proportional to initial speed square, initial velocity square, right? So when the speed is 1 meter per second, the velocity, the distance, stopping distance was 1. When the velocity was 2 meters per second, the stopping distance is 4. When it was 3 meters per second, the stopping distance was 9, and so on. So you see that how the stopping distance are related to the kinetic energy, and which in turn can be proved from the work energy principle. Okay, all right. Now, the next thing I'm going to talk is the potential energy. So there are 3 types of potential energy we are going to learn in physics 1 and physics 2. Okay, so in physics 1, we are basically learning gravitational potential energy and elastic potential energy. Okay, so gravitational potential energy and elastic potential energy in this course, and electric potential energy in physics 2. Okay, so let's start with gravitational potential energy. Okay, and again here you will see that gravitational potential energy somehow related to work done. Okay, Okay, so to understand this, okay, let's consider this picture. Okay, let's say we have a brick at the ground. Okay, so this is a brick. Let's say its mass is m. Okay, so it's on the ground. So because it has mass, you know that it should have gravitational force or the weight, and you know that the weight is m times the gravitational acceleration. So when we have an object whose mass is m, the weight or the gravitational force is m times the gravitational acceleration, right? Now if you want to lift it up, okay, you have to apply force against gravity, right? Because gravity is in this direction. If you want to lift it up, so you have to apply at least this amount of force in this direction, right? So that you can lift it. Otherwise you cannot. If your force is, if your external force is less than mg, okay, then you cannot lift it up. Okay, so to lift it up, you have to at least apply mg amount of force to the upward direction. Okay, and let me call it external force. Okay, so the external force by the hand, this hand, that means someone is applying some force, and this force F external, the magnitude needs to be equal to mg at least, okay, or higher. Okay, for simplicity, let's consider that we need just mg. Okay, all right. So then by applying mg, you lift this brick from this position, y1 position to y2 position. Okay, so what we see here, so w, I mean the work done, so I want to know what is the work done this hand does here. So F external d, so d is from here to here, so you see the blue arrow is basically shows us the displacement, and then cosine theta. For the external force, okay, it is the direction, the displacement is also in this direction. Okay, so both in the same direction. That means cosine theta is equal to cosine 0 degree. That means we have just this equation, F external times d. Okay, now what is F external? The minimum value of F external is mg, and let's keep it, and d here is basically the height. So here you see we use h. So normally when it is a vertical displacement, we use height h. Okay, so the work done by the external force is mgh. Okay, all right, now let's rewrite this equation. Okay, so we have w external equal to mgh. Okay, h can be written as y2 minus y1, because this is y2 and this is y1, and this distance is h. Okay, so I can write h equal to y2 minus y1. Okay, now let me rewrite it, mg y2 minus mg y1. Okay, and you see that this depends on the position at y2, and this depends on the position of y1. Okay, and we call this expression as the potential energy. Okay, so this is the potential energy or the gravitational potential energy at position 2, and this is the gravitational potential energy at position 1. So here what we see is the external work done is equal to the change in gravitational potential energy. Okay, so from this equation we can write, and from this derivation we can say that the definition or the mathematical definition of the gravitational potential energy is mgy. Okay, m is the mass of the object, g is the gravitational acceleration, and y is the height. Okay, all right. Yeah, so before I erase, y is the height, right? And now the question is from where we should measure y. Okay, we should measure, I mean, as you learn in chapter 2, to measure height or to measure some distance, okay, we need some reference point. Okay, so if the reference point is changed, the height will also be changed, right? So because of this, absolute potential energy, so like this is not very important in physics. Okay, but even it is not important, but the changing potential energy is very important, because no matter um, what uh, initial position or the reference point you used to calculate the absolute potential energy, the change in potential energy is always be the same. Okay, no matter, I mean, even if you change the reference frame, okay, you will see that the change in potential energy is always the same. Okay, but the absolute value of the potential energy may be different. Okay, so we'll see at least in one problem that the absolute potential energy are different, but even though the change in potential energy or delta PE are the same. Okay, so when you do the problem, it probably make more sense. All right, now here we show that the external work done is equal to the change in potential energy. Again, change in potential energy is the final potential energy. So here you see the final potential energy minus initial potential energy. Okay, now the next thing we are going to learn is a very similar thing. Okay, but the work done by the gravitational force. Okay, so here in this picture you see that the force, the gravitational force, is in this direction. Okay, so when the hand is lifting this brick from this position to this position, the gravity also does some work. So I want to know what is the work done by the gravity, and let me call it WG. Okay, WG means the work done by the gravity. So similarly, you can show that FG and then D cosine theta. So here cosine theta is cosine 180 degree, right? Why? Because displacement is happening in this direction, but the direction of gravitational force is this. So this means the angle between the force and the displacement is 180 degree. That means this is negative work. Okay, so what we get is minus mgh. So the work done by the gravitational force is minus mgh. Similar to the external force, you can show that mgy2 minus mgy1. Okay, and that is equal to minus potential energy at position 2, potential energy at position 1, negative change in potential energy. So the work done by the gravity is equal to negative potential energy, negative change in the potential energy. Okay, all right. All right, so um, so before we move to the next one, the elastic potential energy, so let me briefly talk about these 2 bullet points. So this 2 bullet points says that potential energy is the property of a system as a whole, not just the object. Okay, now here when we talk about the system, for example, in the brick problem, is the brick is the system. Okay, we are not going to do complicated problems, so we are going to do some simple problem. In simple problem, for example, a problem brick. Brick is the system. For example, here in this simulation, the simulation, this simulation you will be going to see now. Here the car is the system. Okay, so basically our system is very simple. Okay, and in this simulation you are going to see that the potential energy can become kinetic energy if the object is dropped, okay, or moved. I mean, if we change the height. Okay, so let's see the simulation, and then let me comment on it. Okay, so here you see that the simulation. So we have a car in a track. Okay, so you see that we can change the track, but I'm not going to change anymore. Okay, so at this point the car is our, I mean, here the car is our system, and here you see the car is at 4.4 meter per second. Okay, and the car is at rest. Okay, so that means this car has only potential energy, right? V0 means the kinetic energy is equal to 0, right? At this point it has mg, y means 4.4. Okay, now if you let it go, okay, so you will see that the height decrease means potential energy decrease, and then you will see that decrease of height is changed to the some value of the velocity. So let's see. So here you see that now at this point when it is at 2.56, so now you see that the height is equal to 2.56, and at this height it has some velocity. Okay, so that means initially when the car was here, it has only potential energy, kinetic energy was 0. At this point here it has both kinetic energy, okay, plus some potential energy, but this potential energy is less than this potential energy, initial potential energy. Okay, and then so here you see the height equal to 0. Okay, and then velocity is equal to 9.287. That means all the potential energy is converted to kinetic energy. So here you see that there is only velocity, there is no height. Okay, so height 0 means the potential energy equal to 0. So what happened to this energy? All the energy we had here at the initial point now converted to the kinetic energy of this car. Okay, so we'll be learning more about this in next class. Okay, so I'm going to stop it here for today. In next class we are going to learn about elastic potential energy, and then conservation of mechanical energy, conservation of energy and power. Okay, so I will see you in the next class.